Hello and welcome to my YouTube channel. In this presentation, we are going to talk about conductivity and mobility of charge carriers in semiconductors. So let's start the video. First of all, let us talk about drift of carriers in the presence of electric and magnetic fields. Drift means movement of carriers. It may be electron or hole, and how the electrons and holes move in the semiconductors under the influence of electric and magnetic fields. So let us start from the atomics, or we can say the smallest entity. So at room temperature, the atoms inside the semiconductors are always vibrating. Not only the atoms, even the lattices inside the semiconductor are vibrating if they are in room temperature or if they are at any temperature greater than the absolute 0 degree Kelvin. Similarly, the atoms in the lattices are also vibrating when the temperature across the semiconductor is greater than 0 degree Kelvin. So, from the above images, we can say atoms and lattices are always vibrating at room temperature. Secondly, we can say free electrons generated due to change in temperature or due to application of any other external energy will travel through these lattices and keep moving randomly. Remember, they keep moving randomly. So suppose we can visualize it like this. Suppose we have an electron, and if the electron has to travel from this point, A point, to B point, okay, it will not be able to travel in a straight line. Rather, it will just enter, get deflected, and then move, and then get deflected, and therefore these electrons will move randomly, okay, inside the semiconductor materials, provided the temperature is above 0 degree Kelvin. Now let us go to the second topic, that is conductivity and mobility. Why these two terms? We are studying these two terms, and what is the importance of these two terms? These two terms play a very vital role to calculate the impedance or the resistance of solid materials. Apart from that, these two terms play a very important role to calculate the current that flows inside any solid material, or we can say semiconductor. The charge carriers in solids are always in motion due to the temperature which is surrounding the semiconductor devices. And these electrons or charge carriers are always in motion even at thermal equilibrium. So even if we keep the semiconductor a constant temperature which is greater than 0 degree Kelvin, or suppose at room temperature 300 degree Kelvin, and this temperature is not changing, even in that case these electrons are moving randomly throughout the semiconductor device. Okay, so these charge carriers are always in motion, they never goes to rest. Second point, at room temperature the thermal motion of individual electron or hole may be visualized as random scattering. So they travel very randomly, there is no defined path, and they are moving randomly just because they are scattered from the presence of vibrating lattices or lattice vibration, impurities, or we can say dopants, other free electrons which are moving inside the semiconductor, dopant ions, and crystal defects. So all these are major factors which actually causes the electron to scatter and move randomly inside the semiconductors. If we want to visualize, remember, electron is always moving randomly from one point to another point, and this motion is totally random. We cannot have a certain path for the electron provided the semiconductor is above 0 degree Kelvin. Now, there will be no preferred direction of motion for group of electrons, and therefore because there is no preferred direction of motion, therefore the net current inside the semiconductor is also 0. We will calculate current only when the electrons move in one particular direction. If the electrons are moving randomly, then they do not constitute current. Current is measured only when the electrons move from one point to another point in a particular direction. So for that, suppose if we apply any external electric field Ex in the direction x, then these electrons experience a net force which is equal to minus QEx. Let us visualize that. So if we apply an electric field which is moving from left to right, okay, then the electrons net movement will be from right to left. And because the net movement of electron is in one particular direction, then we can say that there is a current which is flowing inside the semiconductor. So when we average over all the electrons, this is here we are depicting only one electron. Suppose there are many electrons, then we average over all the electrons, and that causes net motion of group of electrons in minus x direction. So suppose here this is positive x direction, then this is our minus x direction, negative x direction. So if this is the electric field, then the motion will be opposite to that of the direction of electric field. Now, let us continue. Let us go through some equations to calculate the conductivity and mobility inside a semiconductor. Let us start with the very basic equation: force equal to mass into acceleration. This is the very basic laws of motion, or very basic Newton's law of motion. Let us substitute some values. So F can be represented by Q into E. Here the force is applied due to the presence of electric field. So net force is given by Q into E. Instead of M, we will represent that by effective mass M of the charge carrier, and acceleration is given by A. So if we reshuffle this equation, then we can say acceleration A is given by QE upon MP star. Now let us break down the acceleration. Acceleration is nothing but rate of change of velocity, and we can write rate of change of velocity by dv by dt. Small change in velocity with respect to time. So rate of change of velocity. So dv by dt is nothing but equal to QE upon MP star. Here V is representing the velocity of electron. So to get rid of the derivation, let us integrate both the right hand and left hand side of the equation. So by integrating, we get integration of dv by dt gives us velocity v, and integrating QE upon MP star dt will give us QE upon MP star multiplied by t. And this is the average velocity of electrons before any collision. So the above velocity can be assumed for a moving charge before collision. So we can say, suppose the electrons started moving in one direction, and due to the presence of any atom, defected crystal, or lattice vibration and so on, if the electron is collided with the atoms or so, it will get deflected. So we are talking about the velocity between these 2 points. Okay, these 2 points. So that is the velocity of electron before collision, and we can say that is equal to V max, or if we average out this velocity for lots and lots of electrons which are present in this inside the semiconductor, then we can say V average, that is equal to QE upon MP. Instead of time t, we can say tau I. Now reshuffling the right hand side of the equation, bringing the electric field to out. Okay, so we get QI Ti upon MP star into E. Here tau I is the mean time before collision. First thing, this is the time before collision, mean time. So for multiple electrons, Vmax is the maximum velocity attained by charge before any collision. V average is the average velocity of multiple charges before any collision. Here this term mu is representing Q into tau I upon MP star, and mu is called mobility of charge carriers. Hence, average velocity is given by mu into E, which is equal to mobility into external potential applied. So average velocity is directly proportional to the mobility of charge carrier and also the external applied potential. So to achieve higher velocity, you should have higher electric field applied to the semiconductor, which is directly proportional, or it is relevant to the Ohm's law also. So the current density Jx is given by n q square tau I upon MP star into E. And if we take this whole term and represent it by sigma, then sigma is called the conductivity of material. Here from the above equations, it is evident that sigma or conductivity is equal to Qn into mu p, or we can say sigma conductivity is directly proportional to mu p, or mobility of charge carrier present in the semiconductors. Now let us talk about the effect of temperature and doping on the mobility. So how the mobility gets affected due to external temperature or change in temperature and changing the doping. So there are two types of scattering mechanisms present in semiconductors. First is called lattice scattering and second one is called impurity scattering. Let us go through what is the meaning of lattice scattering and impurity scattering. So lattice scattering, in lattice scattering, a carrier moving through the crystal is scattered by lattice vibration. Okay, so lattice scattering causes due to the vibration of lattices, whereas the frequency of such scattering events increases when we keep on increasing the temperature. So frequency of such scattering is directly proportional to the temperature. Therefore, if we keep on increasing the temperature, okay, then the frequency of scattering will increase, and that will cause the mobility to decrease, because more and more scattering will take place, and that will affect the mobility of electron or hole, and overall the mobility of charge carrier will decrease if we keep on increasing the temperature. On the other hand, scattering from crystal defects such as ionized impurities become dominant mechanism at low temperatures. So at higher temperatures, we get lattice scattering. This graph represents how impurity and lattice scattering are affected or generated at different temperatures. So at low temperatures we have dominant impurity scattering, and at higher temperatures the scattering is dominated by lattice scattering. Okay. Therefore, since the scattering probability is inversely proportional to the mobility, therefore the mobility due to two or more scattering mechanisms adds inversely. So the thing that we can note from this above diagram and the discussion is that there are two types of scattering mechanisms in semiconductor materials. One is the impurity scattering, or the first is the impurity scattering, and these scatterings are dominant at low temperatures. And second one is the lattice scattering, which is generated due to the vibration of lattices, and these scattering are dominant at higher temperatures. These graphs shows the effect of impurity concentration in the mobility of charge carriers in different semiconductors. Here first graph is for silicon, second is for germanium, third is for gallium arsenide. So in the x-axis we have impurity. So if we keep on increasing the impurity, okay, in this direction the impurity is increasing, then we can see the mobility which is in the y direction. Okay, in the y direction we have mobility, it keeps on decreasing. Okay, that is what we have derived also, that if we keep on increasing the impurity, the mobility will keep on decreasing, or we can say mobility is inversely proportional to impurity. So higher the impurity, lesser the mobility. And the last graph shows the relation between the voltage that we apply versus the velocity of electrons or holes, or we can say charge carriers. So if we keep on increasing the temperature, if we keep on increasing the voltage for a certain time period, the velocity of charge carriers increases linearly. Okay, so let me just clear this. Restart. Okay, so from here to here we can see the velocity is increasing linearly, and after a certain point or after a certain voltage, if we still keep on increasing the potential, the velocity gradually saturates, or it becomes almost constant. So up to a certain point, yes, if we keep on increasing the potential, the velocity of charge carriers increase linearly, but after that a threshold, the threshold voltage, the velocity saturates, or it becomes almost constant. So mobility of charge carriers decrease with increase in mobility, and even if we apply voltages after a certain threshold voltage, the velocity of electrons or holes stabilizes, or we can say saturates. With this, I would like to end the presentation. If you have any doubts or suggestions, please share your doubts and suggestions in the comment section. If you have not subscribed the channel, then I would request you to please subscribe the channel and share the presentation and video with your friends. Thank you.